Okay, so let's get to trying to find um, subsequences of holomorphic functions, um, and so basically trying to find convergent sequences of holomorphic functions. We're really looking towards proving what's called Montel's theorem, which is an analog of Bolzano-Weierstrass, and then proving the Riemann mapping theorem, which is, in some sense, that's sort of the maybe not the most important, but the most one of the most interesting theorems that you can prove in one variable complex analysis, maybe one that has lots of applications elsewhere. All right. So, what's our goal first? We really want to, if we look at the space of holomorphic functions, maybe on some domain, we're really trying to figure out when do we know that such a set is relatively compact, meaning when do we get that every sequence has a convergent subsequence. That's really what we want. And the convergence, again, as always, is uniform convergence on compact subsets, and it really has to do with said before that this is the right convergence for both continuous and holomorphic functions. So we'll see that this has a lot to do with continuous functions, and we'll actually prove some stuff for continuous functions first. So what do we want in the end? In the end, we want something like Bolzano-Weierstrass, but Bolzano-Weierstrass is for just numbers. And we'll actually use Bolzano-Weierstrass a bunch of times. But what we want is something with the flavor of, if we have a bounded sequence, then it has a convergent subsequence. What's interesting is that while this is not going to be, we're not going to get an exact replica of this for continuous functions, it's interesting that we get a replica of this as essentially the same term for holomorphic functions, which is actually quite amazing. So let's look at some examples and just a couple of examples in for continuous functions of some real variables. So, for example, sine of n times x. So it's a sequence of functions defined on the real line, and they're bounded, right? I mean, it's less than or equal to 1, right, in modulus, or in absolute value. It's all real value. Now, it turns out that there is no interval, or actually any even large set, but definitely no interval, such that there exists a subsequence that even that converges pointwise for this sine of nx. And in fact, you can't even get it to converge almost everywhere if you know what that means. It's basically a sequence for which there is no convergent subsequence in terms of converging at points. You'd have to look at a very different topology. Definitely not the topology that we're interested in here. In the end, we're interested in actually uniform convergence on compact subsets, right? But this thing doesn't even converge pointwise. Another example, slightly less bad, is x to the n. It's and let's just look at it on the unit interval, on the closed unit interval, and this function converges pointwise. It converges to the function at 0 for between 0 and 1, and at 1 it converges to 1. Right? So it converges, but to a discontinuous function. It does not converge uniformly. So those are a couple of examples of what we're dealing with. Both of these are, of course, bounded sequences in terms of bounded functions. I'll say a little bit more about what do we mean really by bounded. So let's start with what do we mean by bounded. And there's really just like pointwise, we can either have this bounded uniformly or pointwise. So we'll say that a sequence is pointwise bounded if for every x in the set, then there is an m sub x, so some bound that depends on the x, such that it bounds fn of x for all n, right? So it bounds everything in the sequence at that particular x, right? But for each x, maybe you need a different m, or m sub x. Now, the sequence is uniformly bounded if you can find a single m, such that you get this bound that f sub n of x in modulus is less than or equal to m, right? So that you can bound the values of the function overall points in the domain and overall n, right? So that would be uniformly bounded. It's really uniform over x, right? Now, here's an example. So this is an example of a pointwise bounded functions. Actually, it converges pointwise. That's maybe something to mention is that if I have a pointwise convergent sequence of functions, then it's going to be pointwise bounded, because at each particular point I have a sequence of numbers, and if it converges, then it is bounded. Therefore, it's a pointwise bounded sequence of functions. So this guy actually converges pointwise. You can figure out what it is. It's simple calculus, but you can also show, and it's also not very hard, and you can figure out exactly how to do it if you draw a couple of graphs. Actually, it is not uniformly bounded. It is there is no uniform bound, even though it converges pointwise, right? So, and it converges pointwise at every, so in particular, it converges for every x, right? But there is no uniform bound. All right. So let's suppose that we want to get some convergence, and at least at some points. Now the issue is was the examples. It was the first example, really, sine of nx. Was that we had sort of too many points to try to get it to converge. It turns out that pointwise bounded is good enough to get pointwise convergence of a subsequence, as long as the set over which we're the set where the functions are defined is countable. So we have this following proposition that if we have a sequence of functions on a countable set, these f sub n's, right, and they are pointwise bounded, right, then there is a subsequence of this sequence that converges pointwise. Okay, and the proof is actually a nice example of a diagonalization argument. So suppose that we give we somehow give an enumeration of x because it's countable, right? So now if we start with f sub n evaluated at x1, right? We look at this sequence, it is bounded because, well, this is a pointwise bounded sequence of functions. So there is the subsequence, and we'll denote the subsequence because otherwise we're gonna take sort of infinitely many subsequences. So we'll denote it by f sub 1k, and then we'll have a subsequence of that, which is going to be f sub 2k, and so on. So we get a subsequence such that this this subsequence converges at x1, which we can do, right? Now, suppose that we've already defined the subsequence. So we've basically done the first step. And suppose that we've gotten through the mth step, and we have a given subsequence, which is always a subsequence of the previous subsequence, that makes where the subsequence converges on all the xj for j less than m, right? So here this subsequence is always a subsequence of the previous subsequence. So it's definitely a subsequence of the original sequence. So if we have that, then we'll just do exactly what we did in the first step. We'll take a new subsequence. We'll call it f sub m plus 1 comma k, and we'll let that be a subsequence of this previous f sub m comma k, right? And we'll make sure that it converges at the x sub n plus 1 point. Now that means, because it's a subsequence of all the previous subsequences, it converges for all the xj as long as j is less than m plus 1, less than or equal to m plus 1. So it's exactly what we're starting with in this inductive step, right? So now we have infinitely many subsequences, and they always converge for the, we have a subsequence like this, and they converge on x1 through xm, right? So none of them necessarily converges on everything. Now, if x is finite, yeah, we're done. It's there's no need to go forward after after finitely many of these steps. We're done. So suppose that x is infinite. That's the really interesting case. So we don't really have any one particular subsequence, but that works yet. But what if we do that we take a subsequence whose kth entry is the kth entry for the kth subsequence that we defined previously, f sub k, right? And this is the diagonalization that I was talking about. Now, if you look at the tail of this sequence, well, it's really the m tail is really a subsequence of the mth subsequence, right? Because as long as m is bigger than right, basically you go to n subsequence, and then we're really just taking subsequences of that, right? So therefore, well, we know that the mth subsequence, the f sub m comma k, that guy converged at x sub m, right? Oops, sorry. And therefore we have that this sequence, the f sub kk, also converges because it's just a subsequence of that, right? So we have a sequence such that f sub k converges at any x sub m, right? All right. So now we have a subsequence of the original sequence that converges pointwise, which is what we wanted. Okay, now that's good for pointwise convergence, although only for countable sets. Now, continuity, it will require some uniformity. Now, we can do, if we have a sequence of functions, we could pick always in if their domain is a subset of the complex plane, for example, then there is always a countable dense subset on which maybe we can find a convergent sequence, right? But to get that this limit is actually continuous, well, that requires some uniformity in the continuity, and that's this definition of equicontinuous. It's basically we have a set of functions, which is really going to be this sequence, and we're going to say it's equicontinuous basically if it is continuous in the same way. So first, it's just like continuity. We define it at a point, and then we're going to find uniform equicontinuity as well. So at a point, so for a fixed x, it's exactly like the definition of continuity, right? For every epsilon, there is a delta, such that whenever y is within the delta ball of x, I get that f of y is within epsilon of f of x. But now there's this added thing. Well, this is supposed to work for all f in S. So it's supposed to be this choice of delta is supposed to be uniform over S. That's basically what equicontinuous means. All right, and then if it's equicontinuous at every point, that's what it that just means that it's equicontinuous at every. We say it's just equicontinuous if it is equicontinuous at every point. All right, now uniformly equicontinuous, it's the same thing, except now it's just the definition of uniform continuity, right? Again, we get for every epsilon bigger than 0, there is a delta, such that if I have x and y in x that are within delta of each other, I get that the values of f at x and y are within epsilon. But now again, this delta is uniform over all f in S, right? So I just pick just one delta that works. It just depends on epsilon. Okay, now if S is a finite set, then this is the same thing as continuity and uniform continuity. There's no difference. You're just saying that this is a set of continuous or a set of uniformly continuous functions. So this is of course interesting only when S is an infinite set, such as a sequence. So for compact sets, we know that continuity implies uniform continuity, and we get the same thing for equicontinuity. So we get as long as we have a compact set, then we get the once we know continuous, so equicontinuous. So once we have uniformity over F, we actually have uniformly continuous, which means that we have uniformity over the domain and over the set of functions. So here's the proposition: if we have a compact metric space, if we have a sequence of equicontinuous functions, right? So this is an equicontinuous sequence of functions, then the sequence is actually uniformly equicontinuous. So suppose, for basically we're going to do it by contrapositive. So suppose that it's not uniformly equicontinuous. We're going to show that there exists at least one point in X where the sequence is not equicontinuous. And it's basically the same proof as if you look at the proof of continuity implies uniform continuity on a compact set. It's exactly the same thing, except now there's this sequencing put into the picture, right? So suppose it's not uniformly continuous, so that means that there is some epsilon such that we can find a sequence of points, really two sequences of points, xk and yk, such that they get closer and closer together, so that they're within 1 over k of each other, and they're always further than epsilon apart for some function, right? So maybe for some of them it would be, but since this is not uniformly continuous, there has to be at least one function in the sequence that breaks this, right? Basically, it's that we're negating so that for all became there exists, right? Okay, so by compactness, we can just assume that these guys converge, and they clearly have to converge to the same point because they get closer and closer. So if they converge to the same point. Why can we do that? Well, that's just Bolzano-Weierstrass, because these are sequences in a compact metric space. They have a convergent subsequence. So find a convergent subsequence of xk, then find using the same indices, find a subsequence, further subsequence, so that yk also converges, and then just replace these sequences, right, with those. So we can assume that they converge to X, right? Now for any delta, this is going to be the delta in the. We're basically going to show that this sequence is not equicontinuous at X, right? So we're gonna, it's supposed to, something was, given epsilon, we were supposed to find a delta, right? So we're going to show that for that epsilon, the above epsilon, there's no way to find any delta. So we're going to show that it breaks for every delta, right? So that there exists becomes again for all, right? So for any delta, we can choose large enough k, such that x sub k and y sub k are both within delta of x, right? And then we look at we first look at this thing, right? So we have that the way that we picked these x sub k and y sub k was precisely so that the values of the function f sub n sub k, right, one of these functions in the sequence was the difference was bigger than epsilon, right? So we have that. And now we just apply triangle inequality. We basically subtract and add f sub n sub k of x, right? We add in that point x, and now we have this inequality. Epsilon bounds this sum from below, and this is a sum of positive numbers, right? So at least one of them has to be bigger than epsilon. Sorry, epsilon over 2, right? So I guess there's a small typo here, but it's bigger than at least one of them is bigger than epsilon over 2, right? So because if you make one of them smaller than epsilon over 2, then the other one has to be bigger than epsilon over 2. In any case, this was no matter how small delta was, right? So there was no way to make sure that this difference is always less than any particular epsilon, right? So again, sorry about that. This should be epsilon over 2. All right, meaning f sub n is not equicontinuous at x, and we're done. So because we were doing contrapositive, right? So we need to, is sort of one of these basic things that we'll need is to get once we get uniformity across the sequence of functions, we'll get uniformity across the space as long as this was a compact metric space. All right.